I'm gonna be doing chapter 1, part 2 of this Qiskit quantum computing textbook. And I wasn't actually playing music the earlier one, so I'm gonna play some royalty-free music on Spotify. Just because, you know, that helps me concentrate a little bit. And let's see if I can. I'm sending it to the right place. That's better, right? Anyway. I'm just checking. Oh, here, let's play this instead. I like lo-fi. That's better for concentrating. Okay. Sorry for the slow startup. Anyway, we are back here. So we just talked about a little bit of bits and how everything in computers talks in ones and zeros, and they're going to go over some exercises. Computation is a diagram. Whether we are using qubits or bits, we need to manipulate them in order to turn inputs we have into outputs we need. For the simplest programs, with very few bits, it is useful to represent this process in the diagram circuit below. These have inputs on the left, outputs on the right, and operations represented by arcane symbols between them. These operations are called gates, mostly for historical purposes. That's weird. Here's an example of what a circuit looks like in the standard bit-based computers. You aren't expected to understand what it does. It just simply gives you an idea of what circuits look like. A, and then something here affects D and C. And then B is connected there, that too. So it's kind of the same for quantum computers. For quantum computers, we use the same basic idea, but different conventions for how we represent inputs, outputs, and the symbols used for operations. Here is a quantum circuit represents the same process as above. Oh, look at that. Fancy, huh? And then measurements at the end. So X gate, barrier, two-poly gate, X not gate. Oh wait, I think this is a two-poly gate, sorry. That's just an X not gate, that's an X not gate. And then barrier, and then measurements. Okay, your first quantum circuit. In a circuit, we typically need to do 3 jobs. First, encode the input, then we'll do some actual computation, and finally extract an output. For your quantum circuit, we'll focus on the last 3 of these jobs. We'll start by creating a circuit with 8 qubits and 8 outputs. Alright, so n equals 8, and q equals n, and b equals n, output equals. Let's run it and see what we get. Oh, it does nothing, okay. The circuit we have called the QC output is created by Qiskit, and using the quantum circuit, this right here, the number nq defines the number of qubits in this circuit. With nb, we define the number of output bits we'll extract from the circuit at the end. The extraction of outputs in a quantum circuit is done by using an operation called measure. Each measurement tells a specific qubit to give an output to the specific outbit. The following code adds a measure operation to each of our 8 qubits. The qubits and bits are both labeled by numbers from 0 to 7 because that's how programmers like to do things. Just labeled by numbers to put and liked. Right. This command. what just happened here? Let's see. Okay, that was weird. Sorry, something looked like it changed. And I don't know what changed, but that looked different. So they're going to run a for loop for I, for j in range n, measure output, and then this will actually give us what that looks like. See? So we're applying a measurement to each qubit. So 0 through 7, which is 8 qubits in total. This is just how things are indexed in computers. So if that's kind of a hard concept, I would look up like IT stuff, and it'll explain further on why it starts at index 0, and then index 7 is actually the number 8. But yeah. Okay, and then this looks like they're going to run a simulator, turn a qubit, or turn the circuit into an object in the back end, and then they're going to print it out as a histogram. Now if you can't see this, I'll turn it to light mode for just a sec so you can see it. So it's a 1% chance of all 8 qubits being 0. So that's like a 100% chance, basically. That's what that means. I like dark mode. The reason for running many times and showing the results as histogram is because quantum computers may have some randomness in their results. In this case, since we aren't doing anything quantum, we just get the results, all zeros for all 8 qubits, with certainty. Note that this results come from a quantum simulator, which is a standard computer calculating what an ideal quantum computer would do. Simulations are only possible for small numbers of qubits, with like less than 30. But they are nevertheless a very useful tool in designing your first quantum circuits. To run on a real device, you simply need to replace the AR simulator with the backend object you want to use. Okay. Since we're at 7:30, I will end this video and then start a new one. We are in chapter 1.4. and we're going to be talking about creating an adder circuit. Okay?